So, what I want to do before I start going into new stuff is kind of recap for you what we've done so far. Okay. In this chapter so far, the big idea that we've been looking at is how do you determine a rate law? Another way to say that is how do you decide what order something is? Is it zero order, first order, second, so on, okay? And we have basically seen two ways to answer that same question. Determine the rate law for this data. We've seen two different ways to do that. If you go to the very beginning of the chapter, we saw problems where you were given a data table that had molarities and rates. And those were the types of problems where you were comparing line by line. You know, from this line to this line, the reactant is being multiplied by 2. From this line to this line, the rate is being multiplied by 4, for example. Okay? That was one way to find a rate law. The second way that we saw was at the end of last class, we did that graphing problem. Okay? I want to make sure that you understand how you recognize what type of problem it is. Okay? The first type of problem had molarities and rates. Compare line by line. The problem that is on the slide just previous to this one, you know it's a graphing problem because you're given a data table that has times and molarities. Okay? That's different from the data tables we saw at the beginning of the chapter. And what I'm going to show you today is a third way to find a rate law for something. Okay? But before I show you how to do that, I've got to go over a little bit of vocabulary with you. Okay? So, first of all, this is a new term, a reaction mechanism. You all probably don't realize it, but most reactions that we perform in the lab or you see out in nature, most chemical reactions on Earth do not occur in just one shot, okay? Most reactions occur in multiple steps, okay? That doesn't necessarily mean they take a long time. It just means there's multiple sort of mini reactions that happen. For example, my final exam on my organic chemistry test, final exam in college, the professor gave us 2 reactants and said, write, or draw actually, because it's organic, so it's a lot of drawing, draw the reaction to form from these reactants how to form aspirin, which is like a 25-step process. And he says, here are your reactants, draw the mechanism for the formation of aspirin. You have 3 hours. Whew. Okay. Needless to say, I did not do very well. Okay? But very few reactions occur in just one step. Some take 2, 3, 4, 5. I mean, some can go as many as 50. Okay, but the point is, anytime you see a chemical reaction, reactants to products, what you're really seeing is just the overall process. We really have not ever seen these individual steps before, and I'm going to show you what that looks like. Okay? This is what a reaction mechanism looks like. Okay? This would be a mechanism that occurs in 2 steps. To go from the original reactants to the final products, this reaction occurs in 2 steps. Okay? Now let's talk a little vocabulary here. Okay? These 2 put together are called a reaction mechanism. Each individual part to that mechanism is called an elementary step. Okay? An elementary step. So this mechanism has 2 elementary steps. Some mechanisms have 3, 4, 5, 10, 15, 50, whatever. This one has 2. Okay? And we're going to do something that we have done before. I'm going to add these 2 elementary steps together. And if you recall, when you're adding reactions together, you can cancel out things that occur in identical form on opposite sides of the arrow. Do you see something I can cancel out? All right, we can get rid of NO3. What else? Okay, one of these NO2s. Anything else that I can cancel out? Nope. Okay. Well, let's now write out what's left over. I've got NO2 plus carbon monoxide gives me nitrogen monoxide plus carbon dioxide. That reaction matches this one. Okay? This overall reaction actually occurs in 2 steps. Now, I would not expect you to just look at a reaction like this and say, oh yeah, I can clearly see that that overall reaction occurs in 2 steps. I wouldn't expect you to know that, okay? I have to give you this information, okay? But these things that we canceled out, they have names, okay? For example, the NO3 that we got rid of is called an intermediate. Okay? An intermediate within a reaction mechanism. It's always something that gets canceled out, but it's not just anything that gets canceled out. For example, that's not an intermediate. That's called something else. In order for something to be an intermediate, first of all, it has to cancel out. But second of all, it must be a product of one elementary step and then a reactant in a following step. Okay. To fall under the definition of being an intermediate, first of all, it has to be something that gets canceled out, but it has to be a product first and then a reactant. It's something that's produced, which is then immediately used up. So even though this other thing is canceled out, it's not an intermediate. It is, in fact, a catalyst. What's the purpose of a catalyst?
To speed a reaction.
Yeah, to speed up a reaction. Okay? Well, folks, catalysts are also not part of the overall reaction. They get canceled out. But in order, if you think about what a catalyst does, if it's going to speed up the reaction, don't you think it would be pretty important to have it there present in the reactants at the very beginning? Okay? So, in order to fall under the definition of a catalyst, it has to cancel out. But a catalyst, unlike an intermediate, is a reactant first and then pops out again somewhere later as a product. Okay. So guys, you will have questions both in multiple choice and free response that are as simple as, here's a reaction mechanism. What's the intermediate? What's the catalyst? That's it. Okay? Nice and easy. So, an intermediate, something that is formed as a product in one step and then used up as a reactant in a subsequent step. An elementary step is just a part of a mechanism. Okay? And guys, this word, molecularity, it's a fancy word that means something very simple. Okay? First of all, this is a term that applies to elementary steps only. Okay? You don't talk about the molecularity of an overall reaction. You could only use the word molecularity if we're talking about an elementary step. And I'll show you what this word means. It's easier to explain if I show you some examples. This is a chart out of your book. Right? First of all, everything that's listed here, it's telling us these are elementary steps. Pieces of a reaction mechanism. Right? If you have an elementary step that has only one reactant, you can describe it as a unimolecular elementary step. The prefix uni means one. Okay. I want you to look at this second one that's down here in this parentheses. Okay. This elementary step has only one reactant, but it's got a coefficient of a 2 in front of it. Okay? That is not a unimolecular elementary step. Because there are 2 moles of this reactant, we would call it a bimolecular elementary step. This is also a bimolecular elementary step. If you get 3 or more, we don't go tri, tetra, we don't do that, pent. Okay, if it's 3 or more, it's just called a termolecular elementary step. 3 or higher. Yes?
Do we have to know this for AP Chem lingo?
Yes, definitely you need to know this. Okay? To be honest with you, this usually comes up in multiple choice. Okay? Because it's just vocabulary. Right? Now, for those of you that have the notes, big star next to this statement. Super important statement. All the way up to today, okay, when we have been determining a rate law, when we were comparing line by line, when we were graphing, did we ever look at the coefficients in a reaction to decide the exponents? Did we ever do that?
No.
Nope. Up till today, guys, I haven't even said it's important for these reactions to be balanced. I don't even care about the coefficients up till today. Okay? We haven't used the coefficients for anything. However, if you are looking at not just any reaction, but an elementary step, if you're wondering, how am I supposed to know if something is an elementary step? They will tell you, this is an elementary step. It will be very clear. Okay? If you are looking at an elementary step only, you may use the coefficients and turn them into the exponents. You can't do that in any other circumstance unless you're looking at an elementary step. Okay? So for example, if you look at this, what's in parentheses right here, the reactant A has a coefficient of a 2 in front of it, so that turns into an exponent. And that's its rate law. Nice and quick and easy. No comparing line by line, no graphing, none of that. Okay. Now I know what some of you are thinking, well that's great, but that's only useful if we're dealing with an elementary step. So how useful can that be? Well, I'm going to show you. There is a term, a rate determining step. Okay, and I have an example down here, but I actually thought of a better example last class. I want you to imagine that you and 4 other people are going to run a marathon. Okay? And the deal is, you have decided as a group that you will stay together no matter what. There's 5 of you. Who decides the pace at which you go through this race. The slowest person. The slowest person determines the rate of the whole group. Okay? When you have a multi-step reaction mechanism that has 2 steps, 3 steps, 4 steps, whatever, whichever one of those steps is the slow one, or in other words, it's called the rate determining step, that's going to determine the rate of the whole reaction. Okay? So, for example, let's look at this mechanism. Okay? And let's just review for a second before we talk about this new topic. All right, here's a reaction mechanism. Tell me one more time, what do you call these individual pieces of the mechanism? An elementary step, okay? In this mechanism, do you see an intermediate? Yes or no?
Yes.
What is it?
Chlorine.
F2 or just F?
Just F.
Okay. You're right. That is an intermediate. Do you see a catalyst? Nope, there is no catalyst in this mechanism. Okay? There is an intermediate, but there is no catalyst. Okay, well, they've also given us not just the mechanism, but they've given us information about the speeds. This is the slow step. This is the rate determining step. Okay, fine. Well, what did I say just a couple of slides back? What's something that you can do for elementary steps that you can't do for anything else?
The rate law.
Write a rate law using the coefficients as the exponents. Okay? Please tell me what the rate law for this slow step would look like. Rate equals what? K
K
times
NO2
to the first power. Good.
F2 to the first.
Okay. And just to make sure it's clear, why is it okay to use these coefficients and turn them into exponents? Why is that okay?
Because of the molecularity.
Because this is an elementary step. You can't do that for anything else. Okay? I'm going to say something that's pretty mind-blowing. You might want to hold on to something. Okay, you ready? We've just written the rate law for the slow step. Guess what? That's also the rate law for the whole reaction.
Whoa.
Okay, maybe that wasn't as mind-blowing as I thought. Okay? I mean, I was amazed the first time I heard that.
Atoms don't exist.
Okay?
It's all a lot.
Let me just explain to you why I think that's such a powerful thing. Think about what we've had to do to find rate laws so far. We've either had to look at a table of data and compare line by line. That didn't take that much time.
It's still a pain.
Okay, fine. Then the second type, that took a long time.
Yeah.
We had to do all this graphing just to find one single exponent, one number. We didn't have to do any of that here. Just because I was told which step was the slow step, I can write the rate law for the whole thing. Amazing. Now, determine the rate law? Good, we got it. What is the overall balanced reaction? Okay, well, we've canceled out everything that can go, so what's left? Alright, 2NO2 plus what? F2 yields what? 2NO2F. I want you to notice, please, that the coefficients in the final equation do not match this rate law. They don't have to match. The rate law, this came from an elementary step. It didn't come from the whole thing. Okay? So, let me just bring this all together. question. Yeah.
Will any exam ever ask us to find which one was slower or faster?
No. If you are, good question. If you are given a mechanism like this, and the question is expecting you to come up with the rate law from this mechanism, they have to give you this information. And guys, this might seem really simplistic to use these kinds of words. Okay, this is the kind of words they will use. Sometimes if it's a 3-step mechanism, I've seen them say slow, fast, very slow. Okay? Or sometimes they'll do this, and they will make it very obvious. Sometimes they'll give you, instead of words like slow, fast, they'll give you rate constant values, but they're going to make it really obvious, like K2 for this second one is equal to 5,315, and K1 is equal to 0.6. That means that's really slow compared to this one. Okay? Usually, I will tell you they put it in words, but sometimes they'll put it in numbers like this. Okay? So, let's just kind of recap here. At this point, we now have 3 methods to find a rate law. The first is that comparing line by line method. The second, most time-consuming, is the graphing one. And you're looking for which plot gives you a straight line. This is the third way. How do you know which way, if the question says determine the rate law, how do you know which method to use? Yeah, it depends on what they give you. They give you a reaction mechanism, you're obviously going to use this one. Okay? What people find the most difficult is distinguishing between the 2 types of data tables. Remember, if it's molarities and rates, that's a compare line by line. If it's times and molarities, that's the graphing kind. Okay.
Collision.
So, we're going to sort of change gears today to finish up this chapter. The last little section really doesn't have any mention of like rate laws or anything like that. The last section in this chapter has more to do with what is physically happening when reactants interact and go on to form products. Okay, so you need to get your minds somewhat out of a mathematical mode and more into like thinking about what the atoms and molecules are actually doing. Okay? And here's the big idea here. Okay? If you were to observe a chemical reaction under a microscope, you would see some very violent things. Okay? It's not a happy little, 2 reactants come and just kind of touch each other. No. They are colliding, crashing into each other. Okay? In order to react. But there's a problem here. Okay? If you were to observe reactants, like let's say 2 reactants interacting with one another, you would see a lot of collisions. But only a small fraction of those collisions would actually go on to yield our products. And the reason why is an energy reason. Okay? It's not enough for 2 reactant particles to come in contact with each other. It's not enough for them even to collide with each other. They must collide with each other with enough energy. And that energy has a name. Activation energy. You should have heard that term in your Chem 1 class. It just means the energy required to get a reaction going. Okay? And I'm going to just throw out a number as an example. This is a ridiculous number, but just for example here. Let's say that in order for 2 reactants to have a successful collision, go on to make products, they must collide with 20 joules of energy. If they collide with 19, that's not going to do it. They'll just separate back out and go on their merry way. Okay, if they collide with 20 or more, okay, then that's probably going to be a successful collision. Right? And this Arrhenius, that's the name of the scientist that studied all of this. Okay? And you should have seen these curves in your Chem 1 class. Okay, this is just a reaction curve. We always put reactants on the far left, products on the far right. And ladies and gentlemen, this symbol, EA, that stands for activation energy. And sometimes, like I've seen a free response question where you had a graph very much like this one, where nothing is really labeled. And they said, draw an arrow on this graph to indicate the activation energy. Activation energy, guys, is always the vertical distance, because energy is on the y-axis, from where your reactants are to the top of that hill. And so we've got reactants on the left, products on the right. You need to know this term right here. It's very small, I know. It's called a transition state. You need to know that term. It means we're not really reactants anymore, but we're not quite yet our products either. A transition state is kind of a hybrid between reactants and products, okay? And you find a transition state at this sort of apex, okay? This is sort of off topic, but if our reactants are on the left and products are on the right, tell me, just by looking at the general shape of this curve, is that an endo or exothermic reaction? How do you know that? Okay, energy is overall decreasing. And that's correct. It is exo. I know that because the energy of my products is below the energy of my reactants. Remember, an endothermic curve looks something like that. Reactants, products. This would be the activation energy from where the reactants are to the top of the hill. Okay? So you just need to know how to read these graphs, what's being represented where. Okay? And one thing we're going to talk about today is the relationship between speed of a reaction, because that's what kinetics is all about. The relationship between that and temperature. And let's read this statement. It says reaction rate should increase with temperature, meaning all reactions should get faster if the temperature is raised. Can you tell me why on like a molecular level? What do you think?
Because temperature is a measure of average kinetic energy, so if you increase energy, that means the particles are moving faster, so they're more likely to collide with each other.
Exactly. Okay? Raising the temperature is the same thing as raising the kinetic energy of your sample. Kinetic energy means motion. They're moving faster. We're much more likely to have not only more collisions, but more collisions with enough energy. So it's actually an exponential relationship, not a linear relationship. As temperature goes up, okay, the number of collisions with the appropriate amount of energy will actually go up exponentially. Now, there's a problem. It says the observed rate is less than the number of collisions that have the minimum energy. Let me translate that into English for you. It means we can still have collisions. Let me go back to that number 20. We can still have collisions where let's say these two reactants collide and they have 21 joules of energy. Is that enough energy to get over that 20 barrier? Yes. But that may not still do it, okay? And the reason is because of what's called molecular orientation. It's not enough for two particles to collide with the right amount of energy. They also have to be at the appropriate angle, okay? Because in order for something to go from two reactants to a transition state to products, the reactants have to collide in a way that's going to allow for bond formation, okay? And let's say, if you imagine my two fists are two reactants, maybe these two reactants colliding like this, at this angle, maybe that's not going to do it. Maybe rotating this one just 90 degrees, maybe now that's at the perfect angle that we can get some bond formation. Okay? So, honestly guys, if you think about it, it's a miracle that reactions happen at all. Okay? Because there's a lot of requirements. They have to collide, first of all. They have to collide with the right amount of energy. And they have to collide at just the right angle. That's pretty amazing if you think about it. Now, there is an equation called the Arrhenius Equation. And essentially, it represents the relationship between temperature, and this is our old rate constant that we've been dealing with all along. Okay? And let's just get our bearings here. Okay, yes, we are going to relate this to a line equation. I'll get to that in just a minute. But K is our rate constant that we've been seeing throughout this chapter. This A over here is something called a frequency factor. I'm not even going to spend any time explaining that because you're almost never going to be dealing with this. Okay? Again, this equation is on your equation sheet. Alright? EA is your activation energy. Energies are in what units? Joules. Okay. If this is in joules, what value for R is absolutely necessary for you to use?
8.41.
Good. 8.314. Remember, the reason for that is because 8.314 is the only value for R that includes units of joules. Okay. T is temperature. What do you think its units have to be? Kelvin, definitely. Folks, I'm going to pull together a concept we've talked about today and put it together with a topic that we talked about last class. Last class, the very small amount of material that we looked at was all about reaction mechanisms. What were the parts of a reaction mechanism called? Elementary steps, okay? And remember that we saw that one of those elementary steps is the slowest one. And we called that the rate determining step. That slow step determines the speed of the entire reaction. Well, guys, let's put that together with the concept of activation energy. It should make sense to you that the reason the slowest step is the slowest step is because it has the greatest energy barrier to get over. Okay. So, and I know this is fancy graphics. Woo! We're getting crazy. Okay. This graph, this is an energy graph for a reaction. Remember, reactants are always on the far left. Products are on the far right. Tell me first, before we talk about anything in between reactants and products, is this reaction overall endo or exo?
Exo.
Exo, good. Okay. How many elementary steps are in this mechanism? 3. 1, 2, 3. Okay, good. Tell me which of those 3 is the rate determining step. Why'd you say that one?
It's so slow.
It has the greatest activation energy. If you were answering a free response question, don't say because it's the tallest.
The highest.
It has the greatest,
The greatest.
activation energy.
Becoming.
Okay? Let's talk about a word that we learned last class. Let me remind you of the definition of the word intermediate. In a reaction mechanism, an intermediate is something that is a product of one elementary step, and then it becomes a reactant in the next step, or in a following step. It doesn't have to be, but anyway. Where on this curve are you going to find a product of one step, which then becomes a reactant in a later step?
After the first
The
step.
graph dips.
Where the graph dips. You got it. You can have more than one intermediate, that's okay. And think about it. If these are my reactants, aren't the products of the first elementary step right there? Say yes.
Yes.
That's also where the reactants of the next step are. Okay? So your intermediates are in the valleys. Okay, this is a term we learned today. Transition state. It means that hybrid between reactants and products. Please also know this term. They mean the same thing. Where are they? Peaks, valleys,
Valleys.
peaks.
Because I'm more independent.
Okay? An activated complex, also called the transition state. Remember, those are hybrids between reactants and products. Where are reactants and products? It's going to be in between them. Okay?
Maybe a English one.
Okay. Let's wrap this up by talking about catalysts. Okay? First of all, you know from Chem 1, a catalyst is something that speeds up a reaction. It's not consumed in the entire overall reaction. Okay? If any of you have already taken AP Bio or you go on to take AP Bio, Dr. Fernandez will never use the word catalyst. Never. She will always use the word enzyme. Ladies and gentlemen, an enzyme is a catalyst. Why do we have two names for the same thing? Because chemistry and biology like to have their own set of things, their own set of terms. Okay? An enzyme is just a catalyst, but in a specific setting. It's a catalyst in a biological setting. Okay? So make sure that is clear. But someone asked me the relationship between these two. Are all catalysts enzymes? No.
Are all enzymes catalysts?
Are all enzymes catalysts?
Yes.
Yes.
That's different.
Let me give you a real-life example of a catalyst that you interact with every day. You probably just don't even realize it. Okay? There is a part of a car called a catalytic converter. Do you know where that is in the car? It's not under the hood. It's in the exhaust. Okay? It's in the exhaust system. It's in the tailpipe. Alright? There are things in your tailpipe that change the gases that are emitted from your engine into other gases. The gas that is emitted from your engine is carbon monoxide, CO. Okay? There are things in the tailpipe of your car that convert it to CO2, carbon dioxide. There is a catalyst in the tailpipe portion of your car that makes that reaction go faster. Do you know what a catalytic converter is made of? How about if I tell you that it is very often stolen because it is very valuable?
Gold.
It's not made of gold, it's made of a metal more expensive than gold.
Rubidium.
Platinum. Platinum. Here's the reason why I'm bringing this up. If all of the reactants and products in this reaction that's happening in your tailpipe, they're all gases. Platinum is what? Solid, liquid, gas, what?
Solid.
Solid. It's just a strip of platinum. Okay? If your catalyst is a different state of matter than your reactants, that is called a heterogeneous catalyst. A solid catalyst working with gaseous reactants, that's a heterogeneous situation. If my catalyst were made of a gas, then I'd call it a homogeneous catalyst. Okay? And here's the thing. You should recognize this graph from Chem 1. Why do catalysts make reactions go faster? Because they lower the activation energy. They provide an easier path for reactants to turn into products. Okay? All they do is provide a new pathway. The activation energy is lowered. Please notice that does not have any effect in the overall change between reactants and products. Is this curve endo or exo?
Endo.
Endo, good. Now, to be honest with you, this last little piece, probably not on the AP exam. I just think it's interesting because I majored in biochem, and this is a very biochem kind of thing. Okay? I want you to understand physically how a catalyst provides an easier pathway. And it's so cool. Okay? I'm going to draw what's going to look like a big letter E on the board. It's not a letter E. It might look like a letter E. It is not. Yeah, I know. You think it's an E, right?
It's a W. Turn to the side.
It's not an E.
It's an enzyme with active site.
It's an enzyme. And yes, isn't it funny, a coincidence? It's an enzyme with the shape of an E. Ha ha ha.
Enzymes are lame. I'm talking about catalysts.
It's a sticky one.
It's an enzyme.
Oh my god.
And there are two reactants that are going to interact here. And one of them is shaped like this. That's reactant number 1. The other reactant looks like this. Alright, so here's the deal, guys. I want you to think of an enzyme or any catalyst as like a matchmaker. Oh, that's so romantic, isn't it?
DNA.
I want you to imagine, listen, these are your two reactants. And in order for reactants to have a successful reaction and go on to make products, let's think to the very beginning of today's class. What has to happen? They have to collide. What else?
Right angle.
Right angle and?
Right amount of energy.
Okay. If this enzyme were not here, these two, would they ever collide? Yeah, probably. Okay. But it's not going to happen that often. Do you see that this piece fits very nicely right there, and this piece fits very nicely right there? Those are called active sites. They're like pockets that are perfectly fitted for those reactants. Do you all agree that this enzyme, if these two pieces go there, that those two reactants are now being brought in close proximity with each other? Yeah, that's making a collision much more likely. Okay? This is how catalysts work. They are like matchmakers. They provide a way for reactants to more likely interact. Okay? Isn't that cool? I think that's really cool. Okay. Now, let me explain this last thing, and this is the last topic. This is the last thing I'm going to say today. This is a ridiculous example, but I want you to imagine that I have a big beaker that has lots of reactant 1, lots of reactant 2 in it, but I have only added one single molecule of this enzyme. Just one. When these two reactants are in there and the enzyme is doing what it's supposed to be doing, can it help any other pair of reactants? No, it's busy. It can't help anybody else. It's working with this couple. It can't work with anybody else. Okay? If your enzymes are all filled up They're all occupied. You can add as much reactant as you want. Add reactants until the cows come home. You're not going to make the reaction go any faster. And this is what you see. For a little while, ladies in the back, listen. For a little while, you start to see the speed of the reaction increase. Okay? Because you're slowly but surely filling up these enzymes. When you reach a certain point where all the enzymes are occupied and they're all working at maximum capacity, you can keep on adding as many reactants as you want. It's not going to make the reaction go any faster. Okay? Rate increases until all of these active sites are filled up. And then from that point on, you're not going to be able to change anything. And that is by definition zero order. Adding more reactants with no effect on the rate. Okay? I thought that was kind of cool. That is it for the lecture portion. What I would like to do now is give you some help with one of the homework problems. If you have started the problem set, which I hope you all have, please take out wherever you're working on that problem set. We're going to do a problem together. This is number 71 in the problem set. Might I recommend that you do this one? It's very important. Yeah. Okay, let's look at what we've got here. By the way, those of you that have started the problem set, you've probably noticed that this kind of a thing is written in every problem. It's just extra information. You don't even really need it. Okay? But we've got a data table, and then we're asked to calculate something. And it doesn't explicitly say this, but you need to find the rate law before you can answer this question. So we've been dealing with this a lot in the beginning of the chapter. You've got a table of data, and your objective is to find the rate law. Let's first decide what type of problem it is. We have concentrations and rates. What type of problem is this? Is it a graphing problem? No? It's a chart comparison. It's a looking at line by line kind of deal. Alright, well first of all, let's write out sort of our skeleton rate law. Rate equals K times our first reactant. Here's our second reactant. And our job is to come up with the exponents for each one. Okay? Let's start with the first reactant. Which two lines, or what are you looking for? For NO. The O2 has to be what? The same, yeah. Whatever reactant you're focused in on, that one needs to change, and the other one must remain constant. So, which two lines should we compare? First and second, sounds good. What is happening from here to here? Times 3, okay. Staying constant, it has to. What's happening from here to here? If you ever are not sure, okay, if you're not sure, like, if I just look at this, that doesn't immediately jump out at me. It's like, oh yeah, that's going to be times 9. You could always do this number divided by that one. You're going to get 9. Okay, so 3 to what power equals 9?
3.
2. So we've got the first exponent. Let's move on to the next reactant. We need O2 to change and NO to remain constant. Which two lines you want to pick? Why can't you?
NO2 is a constant.
There's no place where NO remains constant. That's why we're doing this problem, because it's tricky. I don't know what this exponent is. I'm going to call it x, because I don't know what it is. It's going to be some whole number, but I don't know what it is. Well, here's what you do in this situation. Please tell me 2 lines where the one that we're concerned with, where O2 changes, and I don't care what happens to the other one. All right, 2 and 3, sounds good. Here's what we're going to do. At this point, this is what our rate law looks like. I'm just rewriting it. NO is to the 2nd power. O2, we don't know. Lines 2 and 3. Okay, great. Well, it doesn't matter what order you do this in. I'm going to rewrite this rate law, and I'm going to plug in numbers from the 2nd line. So, the rate is this. Rate equals k, because we don't have a number for k yet. Times, fill in the numbers, 3 times 10 to the 18th squared times 1 times 10 to the 18th to the x power. Okay? I'm going to rewrite that rate law the exact same way, except this time I'm going to put in numbers from the 3rd line. Wait, sorry, hold on. I wrote the wrong number.
I'm doing it.
Write them right on top of each other. I am going to divide them, which looks really complicated. It's actually very simple. If this is one big fraction, right off the bat, I see something I can cancel out. Okay, gone. Don't have to worry about it. We're going to do this piece by piece. Please put into your calculator just this first part. This divided by that. Tell me what you get. Okay, I'm going to keep that equal sign. K is gone. Put just this part that I've circled. Put that in your calculator. Tell me what you get. There we go.
1.44. Alright, I got that.
Okay. Next, put just that part in your calculator.
Wait.
Okay. Alright. Well, let's think algebra here. Okay, our ultimate goal is to figure out what x is. Just basic algebra, what do you think the next step is that I'm going to do here? Okay, divide both sides by 1.44. And this is what comes up in my calculator. What's the exponent? 1.
Not exactly.
Well, guys, don't make this more complicated than it is. Remember, that exponent, if they're giving you a problem like this, the exponent is going to come out to be some kind of a whole number. What if you ended up with this? What would your exponent be? 0. What if you had that? And you might get one that's a 3, but honestly, I've never seen one 3 or higher on a problem like this. Okay? So I'm going to go back. I now know this is an exponent of a 1, and that is my rate law. Okay? Now, that's not the end of the problem. You still have to solve this, okay? But that's the hard part. That's the part I wanted to go over with you. I want to make sure you understand why this was necessary. If any of you have been using the solution guide at all, they use this method for every single kind of problem like that. I find that to be totally unnecessary. Okay? The only time that this method is absolutely required is if you have a situation where you're doing a compared line by line kind of problem, but one of your reactants never stays constant. Okay? This method is absolutely necessary if you have that situation.